In this lesson, we're continuing to talk about potential energy and focusing on elastic potential energy. Here are your objectives. So recognize that elastic materials, like a spring, can store potential energy, and they do that when you compress or stretch them. So let's say that we had a box here at the end of a spring that was attached at the other end to the wall. And this is our initial position right there. That's where the center of the box is. Now, we could stretch that spring out and bring the box over to this position, or we could compress it and bring it into this position over here. And in either case, the spring is going to try to return the box and the spring to its initial position. And in fact, the force that we need to use to hold the box in either of these positions depends on how far we extend it or compress it. If I were to bring the box all the way out to here, I would need to use a greater force to hold the box out here than at this less extended position. In fact, the further you try to hold the end of a spring from its resting length, and that's called its equilibrium position right here, the greater the force you must use. Let's take a look at that on a graph. On the y-axis, we have the force needed to hold the spring in place, and on the x-axis, we have the displacement of the end of the spring from resting length. So again, we are moving the box and the spring out from the original equilibrium position, the resting length. And it turns out that the force needed to hold a spring at a particular length away from the equilibrium position is directly proportional to how far you want to stretch or compress it. So that to hold the box at the equilibrium position there takes no force at all, that's the resting length. If I wanted to bring it out here, let's say that distance was 0.5 meters, and that took a force of F, then to bring it out to a full meter would take a force of 2 times that force, and to bring it out to 1.5 would take 3 times that force, etc. Introducing some symbols, if I call the force required to hold this spring at a given length F, and I call the displacement from the resting length delta x, we see that F is proportional to, that's what that sign means, delta x. It's directly proportional to delta x. So the force required to hold the spring in place is directly proportional to the displacement from the spring's resting length. Again, the force that I'm applying is proportional to delta x. Now, when we have a statement of proportionality, we can turn that into an equation by adding a constant of proportionality. Let's introduce the constant of proportionality, k, and we're going to call that the spring constant. The statement of proportionality then becomes this equation. The force I need to apply to hold a spring at a given displacement from resting length is equal to k, which we're calling the spring constant, times that displacement from resting length. By the way, notice that this is in the form y is equal to m times x. This is the y variable from the graph above. This is the x variable from the graph above, and that means that k is the slope of this graph. The spring constant, this new constant we've introduced, is the slope of this graph. If the graph were steeper, like this, it would have a greater value of k, and that would mean that it requires more force to hold it at any given displacement from resting length. This would be a stiffer spring, and one with a greater value of k, greater value of the spring constant. And similarly, if we had a less steep slope, it would be a less stiff spring. This relationship is called Hooke's law, after the scientist who described it. In summary then, the force required to hold a spring at a displacement delta x from equilibrium is given by k times delta x. Now, the work done by the external forces to stretch or compress the spring, so the work done by my hand, is stored as elastic potential energy in the spring. So let's talk about that potential energy next. First, recall that work is the area under a force position graph. So if we go back to the graph above, where we had the force applied by my hand on the y-axis and the displacement delta x on the x-axis, and this was our graph, then the area under this curve should be the work that has been done on the spring, and therefore the potential energy stored in the spring. So let's think about how to figure that out. Well, the base of this triangle is just delta x. And the height of this triangle is the force applied, or the external force. Now, by our Hooke's law above, that's equal to k delta x. And therefore, the work done by external forces, or the work done by the applied force, is equal to half times the base times the height, which is equal to half times delta x times k delta x, or 1/2 k delta x squared. And that's the potential energy, the elastic potential energy, stored in the spring by this force, holding it at this displacement. Elastic potential energy is equal to 1/2 times k times delta x squared, where k is the spring constant and delta x is the displacement from equilibrium. So that's an introduction to elastic potential energy.